Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel for everything I want to talk about science and math. And today we're doing physical science, and we're learning about atoms and the periodic table. So that's our beginning there. Okay, so most of this you guys already know, and you're going to see that this is going to be a very easy unit. So first of all, scientists need to be able to communicate with other scientists all over the what? World, right. Let's see if we're on here. Nope. Oh, I'm going to do red. Okay. Even though they speak different what? Languages, yes. See, I told y'all this was going to be easy. Languages. Now, how do they do it? The periodic table. Okay? And what the periodic table does, it lists the elements of pure substances. You cannot break these down anymore. Now, I added to y'all's notes right here that what we're going to be talking about are ways to classify matter. That's, stuff. And there's different ways, but one way to classify matter is by the periodic table, okay? So the elements in the periodic table can't be broken down and still have their properties. So like gold atoms, they're shiny, they're yellow, they're malleable, they conduct, they can be drawn into wires, they're ductile. But if you break down gold atoms anymore, then you get protons, neutrons, and electrons, and those are all the same. They don't look any different, gold protons, neutrons, and electrons, than carbon ones do. Okay? Everybody follows that? So each one has a symbol made of an upper case letter, sometimes followed by a lower case letter. So it's got to be uppercase and lowercase. It cannot be in cursive like that. You have to print. It cannot be like this, a big capital A and a little capital G. That's wrong. It can't be like this, a big lowercase a and then a lowercase g. It's got to be a capital and then a lowercase, not cursive. Any questions about that? Okay, good. All right, so that's our example. So now you can write for an example your element you did a report on. Everybody write for your example the symbol of your report. I'll do H since that's number one. Okay? Good with that so far? Everybody good? Okay, well, we're moving on. Okay, next, atomic regions. The center of the atom is called what? Y'all know this already? It starts with the N. What's the center of the atom called that starts with the N?
Nucleus.
Nucleus. Somebody said it.
That was me.
Yay!
Wait, you took credit for someone else's.
The nucleus. And in Latin, that means little nut. So there's like this little nut of matter in the center of an atom. It's the nucleus. It's surrounded by electrons, and they hang out in clouds. So here, where we think of an atom, where the electrons are in these little discrete paths, they're not. They really just buzz around everywhere in a cloud, but in levels. We'll talk about that in a second. So atomic components. Atoms are made of subatomic particles like protons. And let's check your prior knowledge. What charge are protons? Positive. What charge? No, this one's tricky. What charge are neutrons?
Negative.
Not negative.
Neutral.
They're neutral, yes. Neutral. They have no charge. No charge. And now this one, you should get what charge are electrons? Negative. Negative. So the protons and the neutrons are both in the nucleus.
You said proton, neutron, and nucleus.
Protons are positive, neutrons have no charge, electrons are negative charge. Protons, they live in the nucleus. The neutrons also live in the nucleus. but the electrons live in the clouds. The symbol for proton is a lowercase p. It's why we have to be careful, because there's an element that's an uppercase p. Do y'all remember which one it is?
Phosphorus.
Phosphorus. Lowercase n is neutron. There's an element that's uppercase n. Do you remember it? Nitrogen. So we have to be careful about that. An electron is lowercase e. This is to help you remember. Protons are positive. I have a shirt that says, be like a proton, be positive. I'll have to wear it. Then neutrons are neutral. See the neutral face? And electrons, there's his little negative face. He's a bad electron. There are other subatomic particles like quarks, there's gluons, and all these other things, but you'll learn about those in physics if you take physics. But there's a bunch of, and they're always discovering new ones. But so this is a big area of physics, is discovering these other itty-bitty things that are smaller than protons and neutrons. If an atom has no charge, the number of protons and the number of electrons are the same, so they cancel each other out. And it makes it neutral, because the protons are positive, the neutrons are negative, the electrons are negative, and then they cancel each other out. So we have sort of a little math equation, we'll talk about that, but the atoms are neutral, okay? So remember, when it's called atoms, we're talking about neutral ones. Later on, they actually can get charges, but they're called something different. Okay? All right, so far I'm not going too fast. We good? Okay. Next, atomic number. Atomic number, let me show you what I mean by that on this periodic table. The people in YouTube land can't see. I'll show it to them on this. The elements have a whole number. You see here the whole number, number 1, number 3, number 11. Those numbers is called the atomic number, and it's equal to the number of protons. I know. Will you go let her in? It's what makes certain elements that element. So what makes hydrogen is it has 1 proton. What makes lithium is it has 3 protons. You can pick up the notes under there, over there. Okay. And you missed some, but we'll get you caught up. Okay, so for example, everybody look at the periodic table here. My ruler. That's okay. All right, everybody look. Where's my example? Carbon. Y'all got young eyes. Can you see what that little blue number is? What is it?
6.
It's a 6. So carbon, and you can see it over there. Everybody see carbon and see the blue 6? So carbon has 6 protons. So its atomic number is what? 6. Okay, now look at neon. You see neon is right here. What number is neon? 10. Everybody see that little blue 10 on Ne? So neon has 10 protons. So what's its atomic number? 10. So try one more. Hydrogen, what number is hydrogen? 1. It's like SpongeBob. He's number 1. So its atomic number is 1. Yes? The last one up here? It was atomic number is the number of protons. It's what makes that element. What makes hydrogen is it's got 1 proton. Okay? Everybody get with atomic number. So now we're going to talk about atomic mass or weight. On Earth, mass and weight correlate. So electrons are so small, we don't count them in the mass. They're so small, they don't really weigh much enough to count, so we don't count them in the mass when we're figuring this out. Okay? The atomic mass you get by adding up the number of protons plus the number of neutrons. The proton, you don't use the electrons, it's protons plus neutrons. And here's our little math formula. I told y'all we'd do a little bit of math today. Mass equals protons plus neutrons, okay? So that's the weight. Now, so that means, turns out that not all elements have the same number of neutrons. They can have more or less neutrons. So atoms can have more or less neutrons. And so you can think of neutrons like fat, and elements can be fat or thin. So here's a picture of my two cats. That's Tigger and that's Ruby. They're also on the wall over there by the periodic table. You can see them. Tigger's an orange cat. Ruby is black and white if you want to color them correctly. So Tigger is very thin, and Ruby is very fat. And they eat the same thing. The difference is exercise. He runs around all the time. She just lays around. So it's a cautionary tale about the need for exercising your life. But it's also, are they both cats? Yeah, they're both house cats. The difference is fatness, right? So that's the same thing with our elements. They're still the same element. They're just fat or thin. So haven't you wondered why those cats were on the wall? Now you know, they are representing isotopes, fat and thin atoms, okay? So for example, how many protons does carbon have? We just talked about it. 6. Carbon has 6 protons, but it can have 6, 7, or 8 neutrons. If it has 6 protons, it has a special name that comes from adding up the protons and neutrons, so it's called carbon-12. Carbon-12 is one isotope of carbon. If it has 7 neutrons, then it's 6 plus 7. What's 6 plus 7? 13. And it's called, you guessed it, carbon-13. If it's got 8 neutrons, what's 6 plus 8? 14. And its name is carbon-14. And it's so fat that it's unstable and it's radioactive. That's the symbol for radioactive. Whoop. We're filming sound effects.
What is it?
It's radioactive. Carbon-14 is so fat, it's unstable. And we're going to do a computer lab where you learn more about the range of stability. Okay? So on the periodic table, the mass, or the weight, it used to be called, is this red decimal number down at the bottom. Do you see on that periodic table the red decimal number? I'll show everybody in YouTube land. It's that little bitty decimal number down at the bottom of the element there. And it turns out that there aren't any real elements that have this mass. Because if you notice, these masses are whole numbers. They're the protons plus the neutrons. Everybody understand that? So where this decimal number comes from is it's an average. Imagine you're averaging your grades, and you got a 70, an 85, and a 92. You add them all up and divide by 3. More than likely, it will not be an even number. It's going to be a decimal number, right? It's going to average them. So that's why the periodic table, the masses, have decimals. Is because they are averages. They are averages. Does that make sense to you? Can you understand why they're decimals and in reality they're not decimals?
Yeah.
Okay. All right, so one thing that makes science hard is the words. The vocabulary sometimes is confusing. And this is one thing that's a little bit confusing. So isotopes are fat and thin atoms, but they're all the same. So everybody, if you get stuck and I say, I'm being fat, so you think I'm a fat isotope or a thin isotope, okay? But there's also another thing that starts with the letter I, and that makes it confusing, and they're called ions. Ions and isotopes are two different things. Isotopes are fat and thin, but ions are charged atoms. Atoms, it turns out, can gain or lose electrons. Remember how the electrons are on the outside? They can rub off. And probably some of you have done this before. If you ever taken a balloon and rubbed it on your hair, it made your hair stick up, or you stuck the balloon on a wall and it stuck because you rubbed it on your hair, or you shuffled across the floor in your sock feet and then zapped your brother with it. Anybody ever done that?
Yes.
Besides me? I have. My brother was a little annoying back in the day, and I have rubbed my feet on the carpet and shocked him on the ear. I should probably feel bad about that, but I don't. All right, he's on YouTube too. He sells Rolex watches on YouTube. All right, atoms can gain or lose electrons from their clouds. Remember, if the number of protons and the electrons are equal, it's neutral. So therefore, first of all, we have to follow the thinking here. What charge do electrons have? Positive, negative, or neutral? Which one are they? They're negative. So electrons are negatively charged. So if an atom gets more electrons, do you think it will, remember electrons are negative, do you think it will be positive, negative, or neutral if it gets more electrons? It's going to be negative. So if an atom gains electrons, it becomes negatively charged. See our little negative electron there? Okay, so can I scroll?
Yes, ma'am. It's cold in here.
Yeah, but it's hot in Miss Raymond's room, and I'd rather it be cold than hot. If it's hot, y'all just fall asleep. Cold, at least it keeps you awake. All right, can I scroll all the way up to page 3? Okay, so imagine this now. You've got an atom, and it loses some of its electrons. You're rubbing off some negative. What charge will it be now? Positive, yes. If an atom loses electrons, it becomes positive charge. If it becomes charged either way, it's called an ion. So this is your little thing to help you remember. Y'all like to charge your phones. I got one charging right now. Everybody imagine the word ion on your phone so you can remember that an ion is a charged atom. An isotope is a fat or a thin atom. Can you remember it, even though they both start with the letter I? It's a little confusing. Okay, so there was a guy named Bohr who a long time ago thought of a way to represent electrons, protons, neutrons, and you're going to learn it. It's one of our little skills in here. You can draw a diagram of an atom called the Bohr Model that shows, let me make sure I'm putting it the same way, the number of protons and neutrons in the nucleus and the number of electrons in the different levels of the electron clouds. Okay, so this is something new and it's fun because sometimes school is boring and you just learn the same things over and over again. So this is great. You're going to get to learn something new. So we're going to make some Bohr models. Okay, this is the nucleus. So what you do is we're going to put a plus for every proton. So looking at the periodic table, how many protons does helium have? How many? 2, right? So everybody, this is our nucleus. Draw 2 pluses. Those are our 2 protons in the nucleus. Now, the mass over here is 4 point something or another. But we're going to round it off to a whole number because remember that's just an average. And so we're going to round it off to 4. Is everybody cool with that? It's like 4.02 something, but we're just going to round it off to 4. And now we subtract. What is 4 minus 2? 2. And that's our number of neutrons. So we're going to draw 2 zeros because zeros have no charge in our nucleus. Come on. Good so far? Okay, so this is an atom, so it's neutral. So now we draw our electron cloud. If it's got 2 protons, how many electrons does it have if it's neutral? 2. And we're going to draw them like this, a little negative sign in a ball. So that is the Bohr model of helium.
Can you scroll up, please? I'm sorry.
Yes? I can scroll up. Oh, not that far. Okay? Now, I've had this on my board. You might have noticed it. But I have a little magnet that is for Bohr models. Okay.
You're hilarious.
So this is my Bohr model magnet. And if I was going to do it for hydrogen, these pluses are the protons. I need 2 of them. These green dots are the neutrons. There's 2 of them. And then I got 2 electrons. Ta-da! There's my Bohr model for helium.
Dude, I got sitting.
That's been there the whole time. Y'all just didn't notice it. It was waiting for this day. Today's this day. It gets to be used. Okay, so let's try lithium. How many protons does lithium have? Look at the periodic table over there. How many does it have? The blue number, Li, is right under H. What's the blue number? 3. So lithium, everybody put 3 pluses in our nucleus. Chris, you're right over there at lithium. If we round off its mass, that red number, to a whole number, what would it be?
7.
It would be 7, because it's 6.9. Does everybody know how to do that? You know how to round it, Brian? Brian, do you know how to round numbers? 6.9 rounds to 7. Now, this is our math. What is 7 minus 3? 4. So we're going to have 4 neutrons. Draw 4 circles. Okay?
Why do you put 4 again?
Because that's our neutrons, and how we know it is we subtract the number of protons from the mass. The mass was 7. The number of protons is 3. 7 minus 3 is 4. Okay, now we're going to put the electrons. Now, so how many electrons do we have? Same as the protons.
3.
3. Now, it turns out that these clouds have a max capacity. And for the first cloud, it can only take 2. The next cloud can take more, so that's where the third one will go. 1, 2, 3 electrons. So the number of how many can go on each one, how many the levels hold, goes like this. We're going to say 2, 8, 8, and we'll say 2, but with some dots, because I said here it only really works through element 20, and 2 plus 8 plus 8 plus 2 is 20. You could put more in that orbital, but this model breaks down after about 20. There gets to be some weird things happening, and it doesn't exactly follow the rules. Okay, so that's what the levels hold. Okay, so now I want you to try carbon all by yourself. Right now, everybody try carbon. Carbon is right over there. It's number 6. You see the blue 6? Everybody try carbon by yourself. And then we'll look up here and see if you got it right. Give it a try.
Carbon.
Carbon. It's right there, blue number 6. See if you can do that one. I'll have to squint to see the mass. But it rounds off to 12. Okay?
What are you doing?
Wait, we doing?
We're doing carbon. You're going to try carbon all by yourself.
But carbon is C, right?
C, it is. So right up there on that second row. See, isn't this fun doing something new? Nicholas, are you with us? Okay. Have you got it? You already did it?
I got it.
All right, so let's give it a try. How many pluses, how many protons does carbon get? 6. 1, 2, 3, 4, 5, 6. How many neutrons does it get? 6, because it's 12 minus 6 is 6. So draw 6 zeros. Okay. How many electrons does it get? 6. Does that mean carbon's evil? 666? You know, you're made out of carbon, so maybe.
What did you say? What did you say?
I said it's 666, so does that mean carbon's evil?
Yeah.
Because you know it's the devil's number.
Yeah.
There you
I know
go.
that.
But you know, we're made out of carbon, so ooh, Okay, so how many goes on the first row for electrons? 2. And how many goes on the second row for electrons? 4.
What are you touching me for?
Don't touch anybody. Everybody keep your hands to yourself.
Thank God. It was a reflex. I'm sorry.
All right, so next, everybody get with that idea. We'll do a lab on this tomorrow, a little activity, not a chemical lab, activity, where you'll get better at it.
Okay.
Okay, so next there's a thing called valence electrons. I say valence. People from New England say valence, I think. If you're from Connecticut and that's how you say it, fine, but I say valence because I'm from Atlanta. Okay, and so we're going to, those are the electrons that are on the outside, okay? So it turns out that these electrons that are deep in the inner levels don't undergo chemical reactions. It's only the ones on the outside, so they're the most important ones. So the electrons that are involved in chemical reactions are the ones on the outside. So we have a nice little picture of outside to help you remember outside. These are called valence electrons. Now you can remember how the periodic table helps us understand how to classify matter. It tells us characteristics of the matter. And one of the things, the reason why it has its shape, you notice it's not shaped in a perfect square or list, is the shape tells us about the atoms. And one of the things about the shape is it tells us how many valence electrons, how many electrons it has on the outside. And how you tell it is you count the number of squares over from the left. So you count how many columns it is from the left, not counting the transition elements, to know the number of valence electrons. So let me explain it to you. So I count over 1 square. Lithium has 1 valence electron. I count over 2 squares. 1, 2. Guess how many beryllium has? Everybody say 2.
2.
Yes! I'm going to count over to boron. 1, 2, 3. Guess how many valence electrons boron has?
5.
3. Okay, let's try carbon. 1, 2, 3, 4. Now, do you see how it says not counting transition? These right here under that purple letter D are weird. So we don't count them. Okay, everybody get that in your head. Don't count these right here where it drops down. So if I was going to do gallium, I skip these. And it's 1, 2, 3. So, okay? We skip the ones under the D. If I was going to do germanium, it'd be 1, 2, 3, 4. If I was going to do polonium, it would be 1, 2, 3, 4, 5, 6. Can y'all handle that?
Yes.
Okay. All right, so there was a guy, Bohr made those the first ones we did. But then there was a guy, Lewis, and he said, you know, if the only electrons that are really important are the ones on the outside, why don't we just draw the ones on the outside and forget about all those others, okay? And so this is called Lewis structures.
Here's what I found.
These electrons can be represented as dots. You put one on each side around, let me see how I wrote this the first time, so I write it again that way. Around the symbol. Okay, so for example, carbon. Carbon is 1, 2, 3, 4 squares over. So we put 4 dots around carbon. And it's like the symbol is like the nucleus and the other electrons, and we're just showing the valence electrons as dots. These are called Lewis structures or Lewis dot structures. So neon, how many dots do I need to put around neon? 1, 2, 3, 4, 5, 6, 7, 8. Now, there's a little bit of etiquette to this, okay? There's just a little bit the way you do it. You go around 1, 2, 3, 4, and now we have to double them up. But if they're on the top, the dots are next to each other. But if they're on the sides, they're on top of each other. On the bottom, they're next to each other. on the sides, they're on top of each other. So they kind of make a little dot box going around it. Okay, so I want everybody to try calcium by yourself right now. Everybody give calcium a try. How many squares over is it? Draw that many dots. Everybody give calcium a try right here, right now. Take a dance break while y'all are calciuming. I get bored while I'm waiting on y'all. Okay, you ready for the answer? How many dots does calcium have? 2. 1, 2. Da-da, da-da. Did y'all get it?
Yes.
Everybody got it right? Brian, did you get it?
Yes.
All right. Okay, last page. The first periodic table was arranged by a Russian guy named Dmitry Mendeleev, according to atomic weight. Stay quiet. Later, it was rearranged by atomic number. At the time he arranged it by atomic weight, they didn't know about the proton, so they didn't know about the atomic number yet. Henry Moseley rearranged it later by atomic number, okay? So he arranged it. I say he discovered it because the periodic table is arranged according to the properties and the patterns of the elements. Those have always been there. As long as there's been atoms, that pattern has been there. He just discovered the pattern. So first of all, a lot of our early scientists were religious. They were very holy people. Y'all learned about that last year in biology. Remember Gregor Mendel?
Yes.
With genetics, do you remember what his day job was?
I forgot.
He was a monk. He was a monk. And then he was doing a little science on the side. Well, Dmitry Mendeleev is not that kind of guy. He was a grad student in Russia, and he'd go to the bars, he'd play cards. He was a wild man, kind of wild, and he started noticing there were patterns in the elements, and he took his playing cards and he wrote the characteristics of the elements on there, and he'd take them to the bar and he'd rearrange them until he finally discovered it. Now, actually, by the time he discovered it, he was still a grad student, but he had settled down, he was married and had a kid. But we can still imagine wild man Dmitry at the bar drinking his vodka and figuring out the patterns of the elements. And you can see today, they still look like little playing cards almost, don't they? In their boxes. That's because it came from him. So anyway, so there's a song that's going to help you remember Dmitry Mendeleev. And it's based on an old drinking song, okay? So a long time ago, people, when they would go to bars, they would sing songs. They'd get drunk and sing songs. This was before karaoke or ESPN on the TVs. That's what people did. They go to bars, drink, and sing, okay? Saying, you've seen this if you've seen Beauty and the Beast. Have y'all seen Beauty and the Beast? You know Gaston's song? No one spits like Gaston. Da, 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 da. That's based on like those old bar songs where people would sing, okay? So Dmitry Mendeleev's song is based on an old bar song, and you've got a part, okay? Your part is Mendeleev. When I do this, you yell Mendeleev. You ready? Let's practice.
Mendeleev.
That was okay. Okay, but we're going to do better. Okay, so here it goes. Who told the elements where to go? Mendeleev. That was your part and you did bad. We're going to do it until you do it good. Brian, wake up. We're singing now. It's going to help us remember his name. Who told the elements where to go? Mendeleev. One more time. We're going to do it till you do it good. Who told the elements where to go? Mendeleev. Who put them down in columns and in rows? Mendeleev. This is the pretty part. Who was willing, who was able to make a periodic table? Who told the elements where to go? Mendeleev. And you can like toast Mendeleev with your non-alcoholic apple cider imagined right now. Okay, so y'all ready? We're putting it all together. Who told the elements where to go? Mendeleev. Who put them down in columns and in rows? Mendeleev. Who was willing, who was able to make a periodic table? Who told the elements where to go? Mendeleev. Okay, everybody toast Mendeleev with our imaginary apple cider, no alcohol in it? Okay, very good. It's going to help you on the test. You're going to say, you're going to be a matching question. You'll go, oh yeah, Mendeleev, that's the answer. All right, let's finish up. You can use the periodic table to know what kind of ion an element will form. You can use the periodic table to find the number of valence electrons. You can tell on the periodic table whether it's a metal, non-metal, or metalloid, which is sort of like a half metal. So there's our little metalloid robot. You can know what phase it is at room temperature. So all kinds of information. And like Mendeleev, you can know what properties an element will have. So once Mendeleev figured out his periodic table, he was able to predict that they were going to discover elements that weren't discovered yet and what properties they were going to have. It was like magic. It was like he was looking into a crystal ball and knowing the future. So we can know those things too. Okay, so how do you know what charge an ion will have? Well, it's this pattern. 1, 2, 3, skip. -3, -2, -1, zip. And it's based on which column it's in. And you start over here on the left again. So they go like this. So their first positive, they are 1, 2, 3, skip, -3, -2, -1, zip. So you skip all of these under D again, because they're weird. We'll learn about why later. You also skip carbon's family, because they're weird too. And it's zip for the noble gases, because as you knew from your reports, they don't form ions. They don't hobnob with regular chemicals. They stay by themselves. So the pattern is, and you're going to memorize it, 1, 2, 3, zip, -3, -2, -1, zip. And if you look at that periodic table, up at the top, you see I've written that in green. Do you see it? And on the test, that'll be hanging there. So use your anchor charts. Use the room. Cheat off of the walls. Okay? All right. So you look at the columns.
No. Sorry.
You look at the columns to know what total charge it will have as an ion. The next bit of information we can know is if it's a metal, non-metal, or metalloids. Metals are to the left on the periodic table, over here. Non-metals are at the top right. They're up there. And metalloids are the stairs, they touch the stair steps in between. So on that periodic table, see the stair steps are orange. On this periodic table, they're black. But the metalloids touch the stairs. Any questions about that? Is that easy to know? Okay, next idea. Phases are room temperature. The phase means solid, liquid, or gas. So for our periodic table over there, the solids are black. The gases are red. And the liquids are blue. Now the white ones are man-made. So they're kind of fake. And a lot of them don't stick around long enough for you to know what phase they are. Okay, so there's our solid, liquids, and gases. Now properties. Okay, so this gives them their properties. Atoms to the left, over on that side, want to lose electrons. The ones on the left want to lose electrons. Atoms to the right want to gain electrons. Except for the noble gases who want no change. Then remember, the noble gases are the ones right down here, and they want no change. All right, that wasn't so hard, was it? Okay?
Hold on, sorry.
What do I always say at the end? Oh, yeah. Science is great. Like, share, subscribe.